So thank you everyone so much for taking time out of your day for this webinar. I hope that it proves useful for you and your colleagues. Let's see, today is exciting for us. It's the first time we have ever had the maximum number of people registering. We received messages unable to register. We'll discuss what we can do for next time, but for today, we have reached the maximum number of registrations. Hopefully most of those people will join and we will have to see. So let me see, I'm sharing my screen. I'm going to the WHONET homepage. So the purpose of today is to get an introduction to WHONET's data analysis features. A few months ago, we had a webinar on WHONET installation, configuration, data entry, and that webinar is available on the website. And the focus today will be WHONET's analysis features. Generally speaking, we have two kinds of analyses in WHONET. Interactive analyses where you are in control. I want to do this analysis today with these filters, with these options. We call that interactive data analysis. The other kind of analysis we call quick analysis. The one-button solution. You hit this button and the analysis gets started. Less flexibility, but greater convenience. I want my weekly report, my monthly report, my quarterly report for different audiences. Okay. So as you saw in the agenda, we will divide the webinar into three sections. A PowerPoint introduction to analysis and its features, its uses, its limitations. Then we will go through each of the different sections about percent resistance and cluster detection and alerts, each of the analysis features. And finally, a very brief introduction to the platforms WHO GLASS from WHO and FAO InFARM from FAO. WHO GLASS obviously focuses on human health. They also do have a project called E. coli tricycle, which also looks at environmental samples. So that's the WHO GLASS initiative. And the FAO InFARM initiative is a collaboration to look at antimicrobial resistance in food and in animals. I mentioned that the WHONET webinars will be available online, and I will show you where to find them right now. Here, if I simply open up a web page, I go to whonet.org, obviously the WHONET homepage. And here on this homepage, you can download the software right here. We discussed that on the last webinar. I'm going to take a look at the menu options. Software, where you can download WHONET, our automation tool, a few other things. Our training center, I will come back to that in a few moments. The webinars, I will come back to that now. The discussion forum, a little bit about WHONET and how to contact us. I will once in a while pause to make sure that there are no questions in the chat. I'm going to do that right now. And there are no questions in the chat, so I will continue. Adam, obviously, if you see some urgent question, just let me know, and I'm happy to take a look. I will not be regularly monitoring the chat, but once in a while, I will take a small break to see if there are any questions. And I do encourage you to post questions, ask questions, and we're happy to address those. I'm back on the WHONET homepage. I will now go to webinars. I've clicked here on webinars. And at the top of the page, you see all of the details for today's webinar, including those three sections. A general introduction, I will do that with the PowerPoint. The three areas for WHONET data analysis. And finally, reporting to WHO GLASS. If I scroll down further on the page, you can see the materials from October, last June, last March. We do approximately one webinar per quarter. We could do more, we could do less, but we might do another one. We might start doing them more frequently. We will think about that. For example, if I click on the October one, you can see here the YouTube webinar, and you can see the PowerPoints that we utilized. You can also see a brief summary of the agenda. So for anyone not on today's call that you think might be interested, feel free to share this link with them. Here is the precise link, whonet.org/webinars.html, but I never remember that myself. I simply go to whonet.org and I click on the webinars menu. I'll now continue with the training center. So the PowerPoints that I will use today are here on this page. So in fact, we don't need to send you the slides because you can access the slides yourself through the training center. It's a self-paced course. If you would like to do the full course, you can watch the videos. They are each approximately 25 minutes long. Presentation number 5 is a bit longer. Eventually, we'll chop that into 2 separate presentations. There are the YouTube videos, there are the exercises, there are the PowerPoints that you can download, and relevant online manuals for you to review if you would like. So on the last section, in the last webinar, we covered 1, 2, and 3. Today, we will cover 4, 5, and 6. We won't cover all the videos and the PowerPoints, but I will draw from those. So today, I would like to focus a little bit on number 1. I'm going to click on the PowerPoint. It's now downloading. It is finished downloading. I can now open the PowerPoint. So WHONET training course, module 1, Introduction to WHONET. Most of this presentation I gave in the last webinar. What is WHONET? We discussed that. WHONET is a free software widely used around the world. It is valuable for clinical reporting. It is also valuable for public health and epidemiology and research. The father of this program is Dr. Thomas O'Brien. He has been my mentor, my inspiration, my friend. We worked together for 36 years, a great privilege of mine. He did pass away in December. Very sorry about that, but very grateful for the collaboration that we had. He was the director of the infectious disease division, as well as the microbiology laboratory. And his perspective was that human, animal, food, and environmental labs generate very valuable information for day-to-day patient care decisions, policy, regulatory work. And that information is very valuable on a day-to-day basis. But the information is also very valuable in aggregate for public health reporting and research and policy. His view was that the use of a common software could and should support local, national, regional, and global collaborations and analyses to support infection and resistance containment in several areas, tracking of new threats, treatment guidelines, awareness, advocacy, policy, and research. In addition, the data are also valuable for continuous quality improvement in laboratory test practices and in the use of the data. Let's see, I'll come back to this point later, but for all of the analyses we will discuss, I always view it from 2 perspectives. Yes, of course, epidemiology, what are the data telling us about resistance and microbes, obviously. In addition, every analysis, there is some quality element. Do these results make sense? Are they testing the correct drugs, or are they testing invalid drugs? Do there seem to be evidence of contaminations? So every analysis we look at, first I will approach it from the perspective of quality assessment, and secondly, from the perspective of resistance interpretation. So the data can be used at all of these levels, local, national, regional, global. I especially want to emphasize the local value. Of course, there is national value and regional and global, but I would like to emphasize the local for 2 reasons. It's at the local level that we take care of the patients and the animals, and we do the water testing. It's at the local level we have new resistance, we have hygiene issues and small outbreaks. It's also at the local level that we need to generate the data. And I hope all of you are on this call, not because WHO or FAO or the UK Fleming Fund has asked you to be on. I'm hoping that you're on the call because you find value for yourself in your own facilities. If there is local value, then this will survive in the short, medium, and long term. If the only reason you're doing this is for the national or regional and global programs, those are important objectives, but there needs to be some value to you as the data generators. So we'll say, well, how can this be useful in your hospital, in your community, with your set of stakeholders at that local level? So both in terms of interventions and assessments and continuity and sustainability, we feel that the local is especially valuable. Reviews these slides on the last presentation. The data come from the laboratory, so obviously staff in the microbiology laboratory are primary users of the software. So for data entry and installation, we teach the microbiology lab staff and a small number of people. But in terms of use of the data, we try to train many additional people. I might train 3 or 4 people in data entry, but I might train 20 people in the use and interpretation of the data. Laboratory, infectious disease, infection control, human, animal health, pharmacy, food producers, environmental scientists, policymakers, researchers, and others. Anyone who might have an interest in interpreting and acting on the accumulated data. I've already mentioned these. There's installation, there's configuration, there's data entry. We covered that in the last webinar. There's backlink. If you already have a laboratory information system, we want to take advantage of that. If you have no laboratory information system, use WHONET to manually enter your data on a daily, weekly basis, monthly basis. If you do have a laboratory information system, we do not want you to do double data entry. We don't want you to enter the data into your own lab system and then immediately recopy the same data into WHONET. That's the purpose of the backlink software, to import existing data. If you have data in Excel or a Vitek or a Phoenix or a laboratory information system, once a day, once a week, once a month, you can utilize the backlink software to transfer the data from your system into WHONET. In this case, WHONET is not your day-to-day system. WHONET is a valuable add-on for a data analysis, data sharing, public health reporting. So now I'll focus on data analysis, the focus of today's webinar, but I'll check to see if there's anything in the chat, and there's nothing in the chat. Let's see. I do see a number of people putting their name and their institution in the right-hand side. Not a requirement, but it is nice. If you would like to type in your name, feel free to do so, and we'll take a look later. Okay, I go back to my PowerPoint. So this screen is the main screen for WHONET data analysis, interactive analysis. In this screen, I am in control. I get to decide those 3 important red questions on the left. What type of analysis, which organisms, and which data files? What does that mean? The top left, which analysis? Do you want graphs, alerts, statistics, tables, charts? What is the type of analysis you would like to do? That's question 1. Question 2, which organisms do you want? E. coli, Staphylococcus aureus, all gram-negatives, parasites. WHONET was primarily developed for antimicrobial resistance to study bacteria and fungi and their resistance. In WHONET, we have also included viruses, parasites, other values such as no growth, normal flora. So WHONET is not only for resistance, it has special uses for resistance, but it can be utilized for other elements of the laboratory data. Question number 3, data files. Do I want to study the January data, the March data, the 2020 data? Do I want to analyze, if I am the National Data Manager, do I want to analyze the data from Laboratory 1, Laboratory 3? Do I want to analyze all of the laboratories together? WHONET, there's no limit to the number of data files you can analyze at once. You can analyze 1 file or 10 files or 200 files. So those are the 3 required questions on the left. What type of analysis, with which organisms, and which data files? With those 3 questions in the lower right, I can click on Begin Analysis. By default, the results will all be visible on the screen, but you can also say Excel, Access, SQLite, or a few other things. So the 3 questions on the left are required, and then in the lower right, you can choose the screen and begin the analysis. There are other options also available on the screen. The most important one, would be this one called Isolates. And that's to introduce filters. Maybe I want all of the Escherichia coli, but maybe I only want the urine, or the intensive care unit, or the poultry, or the imipenem-resistant strains. So I could put a set of filters, such as female, urine, outpatient. That is a very common clinical scenario. So I could do a filter. Maybe I do not want all of the Escherichia coli. I only want Escherichia coli that meet these criteria. I can set that here with isolates. Another optional feature is one per patient. This is extremely important in human health. It's not usually important in in food samples or water samples. Usually we just touch each water or food sample once. For animal samples, most animals only get one sample. Sometimes animals, like large animals, dogs, cats, horses, cattle, might be sampled repeatedly over time. But in human health, this is extremely common. A patient might be hospitalized for 3 weeks. They might have susceptible E. coli a few times and then some resistant E. coli. So if a patient has E. coli 10 times, we recommend you put all 10 results into the database. The resistance characteristics might be the same or they might be different if there is resistance acquisition. So if the patient has 10 Escherichia coli, we want all 10 in the database, but we don't always want all 10 in the analysis. So for example, for annual antibiograms, the recommendation from CLSI and others is to do the first isolate per patient per species. So I want all 10 E. coli in my database, but I only want the first one when I'm doing my national or my hospital annual statistics. There are some other options here on the top right. And then macros. Macros are not required. You do not need to learn about macros, but they have a lot of value and a lot of use to make things easy and convenient for you over time. For example, today, maybe I want to do analyses of these 20 organisms in urine, first per patient, in the intensive care unit. So today, I set up all of those requests. If I want to repeat that same analysis in 1 week or 1 month, if I want to repeat that analysis later, that's where you can use the macros. I have designed all my criteria and I say save macro. WHONET does not remember the results of the analysis, which can change as the data increases, but WHONET will remember what the question was. So I can say today I want percent resistance in outpatient urine from women, and I want to repeat that analysis in 1 month using these macros. So we'll see all of these features today. These are some examples of what the WHONET analysis results look like. One example, which is not listed on this slide, is the analysis called isolate listing and summary. In an isolate listing and summary, you can see a list of every person or animal or food that has an imipenem-resistant E. coli. You can see the list of results from neonatal intensive care units. That's the list. You can also see a summary. How many E. coli, how many urine, how many blood, how many imipenem-resistant E. coli. That's isolate listing and summary. Number 2, you can see in the top left percent resistant, intermediate, susceptible, and histograms. I'm not going to spend a lot of detail talking about each of these now because I'll come back to it later in this presentation. But just a few things from a quality. So right now I'll only focus on quality. For percent resistance, I want to see what are the drugs they're testing. There are obvious mistakes that I have seen. I have seen laboratories test E. coli with vancomycin. That's an obvious mistake. It is resistant. There's no need to test it. It's just a waste of resources. That's an obvious mistake. There are other mistakes that are not very obvious. For example, the CLSI has clinical breakpoints for ampicillin and E. coli, but CLSI does not have breakpoints for amoxicillin. So I do see many laboratories test the amoxicillin disc, but CLSI has no guidelines and no breakpoints. It's a mistake, but it's not an obvious mistake. UCAS, the European system, they do have breakpoints for both ampicillin and amoxicillin. So if I see somebody testing E. coli with the amoxicillin disc, they should not do that. They should test ampicillin, and with ampicillin, you can predict the amoxicillin result. So look at their list of antibiotics to make sure that each antibiotic has breakpoints, has valid testing criteria. The middle screen scatter plot, I am comparing 2 drugs. They might be similar drugs or they might be resistant drugs. I'll talk more about this later, but in this particular example, these are Klebsiella pneumonia. Anything in the first column is resistant to gentamicin. The last column, everything is gentamicin susceptible. If I consider the rows, at the bottom row, you have amikacin resistant. In the top row, I have amikacin susceptible. So if I put those two variables together, I see in the top right, 86% of the bacteria are sensitive to both amikacin and gentamicin. These are both very good drugs. In the lower left, 0.3% are resistant to both, suggesting that one of the two drugs should work. The interesting value here is 10% in the top left. 10% are resistant to gentamicin, but they are susceptible to amikacin. So a few conclusions. Yes, both drugs are very good. 86%, both drugs will work. 10% amikacin is better. It's 10% better microbiologically. 10% of these bacteria, the amikacin should work, but the gentamicin would not. So a correct conclusion is that amikacin has better microbiological efficacy. An incorrect conclusion is that amikacin is better, therefore we should always use amikacin instead of gentamicin. That's an incorrect conclusion because amikacin is usually a more expensive drug and it's a reserve agent. We don't want to give these expensive reserve agents to every person because we will lose their value and efficacy over time. So an incorrect conclusion would be that gentamicin should not be used, we should use amikacin. A better conclusion is that for routine, non-life-threatening, simple community infections, gentamicin should be excellent. If the patient is not getting better, most of the patients should get better. If they're not getting better in 2 days, they should come back to the doctor and we can replace the antibiotic. So gentamicin would be a very appropriate first-line agent for non-life-threatening community infections. But for intensive care unit patients, emergency room patients with sepsis, then amikacin would be more appropriate in that circumstance. I'll talk about other uses of a scatter plot later, but this kind of information is valuable for treatment guidelines to look at first-line, second-line agents and cross-resistance. People look at cross-resistance all of the time with tuberculosis, MDR-TB, but the same concepts apply to any bacteria or fungus. In the scatter plot, we look at 2 antibiotics. In the top right, we look at resistance profiles. We look at many antibiotics. So in this particular graph, these data have been published. We have looked at a particular kind of CRE, carbapenem resistant. Oh, I'm sorry, take that back. That's not this example. This is a certain kind of multi-drug resistant E. coli. It is not imipenem resistant. And we're looking at multiple drugs. So with the multiple drug resistance, it first appeared in hospital B, and then it moved to hospital C, and then it moved to some of the nursing homes. And then the problem basically disappeared from most of the laboratories, but then took off in hospital F. The number of people here is only 5 people, 4 people, 3 people. So the numbers here are very small, but it's looking at E. coli, not in aggregate. It's looking at E. coli with a particular combination of resistances. In WHONET, we call that the resistance profile. We study multi-drug resistance in part because of its clinical and public health importance. These organisms are often very difficult to treat. But we also look at multi-drug resistance as an epidemiological tracker. Of course, the best way to track patient resistance is with whole genome sequence and molecular typing. But that takes time and energy and equipment and funds and the knowledge. We cannot do molecular typing in everything, but we can look at the phenotype. So by looking at the phenotype, I can see there seems to be something interesting and important happening here. There seems to be a growing subclone of E. coli that is growing. If I am very concerned, then yes, I can also do molecular typing. Lower left, WHONET has different kinds of alerts. On the lower left, we have microbiology alerts. On the lower right, we have statistical alerts. Here in the lower left, in red, you see some results that are important or unusual or infrequent or possibly wrong. For example, MRSA would be red, important organism, important results. VRSA, vancomycin-resistant Staphylococcus aureus, would also be very important if it is true, except it is often a laboratory mistake. So, if WHONET shows you red, WHONET says this is unusual or important. WHONET gives you a large set of rules. You can also make your own rules. And the idea is to take some action. For example, if you have Klebsiella pneumonia susceptible to ampicillin, that happens. The large majority of Klebsiella pneumonia are ampicillin resistant, maybe 95%, 98%. If you see a Klebsiella pneumonia susceptible to ampicillin, it might be correct, but it also might be incorrect. So WHONET will show you results here that potentially might require retesting, reconfirmation to make sure that the organism identification was correct and also that the antibiotic result was correct. We categorize these alerts as important species, important resistance, and quality control alert. We also categorize them as high priority, medium priority, and low priority. For example, VRSA would be high level priority resistance, but also quality. It would be very important if it's true, but it's usually a laboratory error. Klebsiella pneumonia susceptible to ampicillin is a low priority alert. It's more educational. Most people know that most Klebsiella are ampicillin resistant. So those are the microbiology alerts. And as I said, you can make your own alerts as well. In the lower right are statistical alerts. We have integrated WHONET with another free software called StatScan. StatScan stands for Space and Time Scan Analysis. The website is statscan.org. You don't need to learn StatScan because we have integrated some of its features into WHONET. So in the lower right, you see Shigella sone, but you don't see all of the Shigella sone. You see Shigella sone that are non-susceptible to SXT. SXT is a common abbreviation for cotrimoxazole, also known as trimethoprim sulfamethoxazole. So as I said, there's not a graph of all of the Shigella sone. It's a subset that are resistant to this one drug. So it's another example where we are using the resistance from the phenotypic perspective to say these look like the same bacteria. And I can see that this happens. These are, I believe, weekly data. I see that these data, Shigella sone, it happens once, zero, twice a month. So it happens. It doesn't happen very often. Until that final period on the right, where they had, I think that's three people in this, or 5 people, it's hard for me to read the axis. There are about 5 people in the same month with the same thing. Shigella sone non-susceptible to SXT, followed by several more. These were found in real time. These were confirmed by PFGE, a kind of electrophoresis. A few years later, they were reconfirmed with whole genome sequencing once they had the ability to do sequencing. So with the phenotype, I cannot say that these are the same bacteria, but it does suggest the need for investigation, confirmation, and action. These particular data are from a publication that we did with Argentina on the use of WHONET StatScan in the community setting. We also applied this in many additional papers for detecting hospital outbreaks. And a key element of what we do is we use the resistance profile as a way of helping us to improve the sensitivity and specificity of cluster detection. The data can obviously be viewed on the screen. You can export to Excel. Some of the results can be exported to Word. Those 3 we will discuss at great detail. In the lower left, we have also integrated WHONET with a software developed by the Oxford Clinical Research Network in Southeast Asia called AMAS. It allows you to look at the routine microbiology lab data. It also has abilities to look at mortality, hospital stay, admissions. So if you have an interest, you can go to the AMAS website. So we didn't do this, but we've integrated so that from WHONET, you can create this document. It's a PDF document. In the lower right-hand side, we also feel very important about the concept of interoperability. I mentioned earlier with backlink. If you have many different systems, you want interoperability on the input side so that WHONET can collect data from a variety of systems. It's also very important on the output side, so the data can be managed and utilized in WHONET, but to export data to other platforms such as WHO GLASS, such as FAO InFARM, such as DHIS2 for public health reporting and data visualization. I think I have the slide as well here. Some examples here at the bottom: GLASS, EARSnet is in Europe, DHIS2, AMAS, MicroReact. I want to update the slide to also include FAO InFARM, which only went live last June, so I need to update the slide to include InFARM. We have done a lot of work to support also the human health sector over the course of my 36 years in the project. But for the last 25 years, we have also been working actively in animal health and food and less in environment. But we are starting to do more work in the environment now with different collaborators. Animal species, production types, the antibiotics, the specimen types, the pathogens. A lot of this has been with input initially from the US Department of Agriculture, Food and Drug Administration, but increasingly, well, and then with WHO for a number of years. And then most recently with FAO and WHOA. WHOA is the World Organization for Animal Health. It used to be known as OIE. So we've had input from individual WHONET users as well as national and international workers in the One Health sectors. The UN Environmental Program. So I mentioned the E. coli tricycle project that is currently led by WHO, but there's also involvement in the discussions of the UN Environmental Program. WHONET supports the CLSI human and animal clinical breakpoints, the UCAST human and animal clinical breakpoints, and the epidemiological cutoff values. This is often known as ECOF. CLSI calls them ECV. It means the same thing. I put MIC results. We need to update that. We also were able to add in the disk diffusion results. So we've done a lot to support WHONET use in the human sector, but also increasingly over more than 20 years in the animal, food, and environmental sectors. I will talk more later about the CLSI and UCAST breakpoints, the difference between the human and animal breakpoints, the difference between clinical and epidemiological breakpoints. I'll talk about that later. So in summary of this portion of the slide, WHONET is a free software used for studying evolving microbial populations around the world. One focus is annual reports, laboratory reports, national reports. But for many people, they stop there. They analyze data once a year. It's a valuable use, but they're missing out on opportunities. We want to support the recognition, tracking, and containment of emerging threats in something close to real time. If there are outbreaks, if there are quality issues, there's new resistance that you have not seen before, you want to confirm that in real time and address it. Similarly, if there's a lab testing quality issue, you want to address and fix that early. So let's see, that's the end of that particular PowerPoint. I'm going to jump to number 4, Introduction to Data Analysis, and look at a few slides from that PowerPoint. While I do that, let me just take a look at the chat. There is nothing in the chat. Okay, that slide set is now open. Introduction to Data Analysis, Module 4. I mentioned first, so I won't do number 5 and 6 using the PowerPoint. Numbers 5 and 6, modules 5 and 6, I will do as a live demonstration. Number 4 is what I will cover in this particular module, an introduction to the concepts. Oh, I changed my mind. Number 4 is how do you select the screens? I will do that as part of the live demo. What I meant to do was number 5, data analysis and interpretation. Number 4 is an introduction to the analysis screen. Number 5 starts off with why do we do analysis? How do we interpret the results? So some guiding principles, that is what I will focus on now. And then specifically, the PowerPoint goes into each analysis. Why do we do percent resistance? Why do we do scatter plots? Why do we do alerts? So using the PowerPoint, I will do A, guiding principles. And then from there, I will switch over to the live demonstration. So as I mentioned earlier, why do we do analyses? We do analyses with 2 objectives. One is to study and act on the epidemiology of changing microbial populations and resistance. And there are different needs at the local, national, regional, and global levels. So you might think of how could this be useful for my laboratory? How could it be useful to the National Control Program? How could it be useful for EARSnet, the European program, or RELAVR, the Latin American program? So we'll spend a lot of time talking about interpreting the data from a microbiological, epidemiological perspective. We'll also talk about quality improvement. Are the drugs correct? Are there contaminations? Are there strange results? And also diagnostic stewardship. Everyone is familiar with the concept of antimicrobial stewardship, the appropriate use of antimicrobials. Diagnostic stewardship is the appropriate use of diagnostic services. For example, many laboratories take a lot of samples from wound and sputum and urine, in part because it's important, but in part because they're easy to do. But a lot of laboratories do not do many blood cultures or cerebrospinal fluid cultures. They're more challenging. But for patients with certain diseases, the blood cultures can be life-saving to diagnose sepsis, which organism, which resistance, to confirm meningitis. So diagnostic stewardship, are they doing a lot of blood cultures or very few blood cultures? And then percent positive. My own hospital, it's something about 10% of our blood cultures are positive. About half of those we consider to be contaminants, and about half of those are real pathogen. But some laboratories, it might be 20 or 30% positive, which might be consistent with high rates of contamination. I want to focus here for a moment on bias. This is extremely important. One of the most common desires to use antimicrobial resistance data from a laboratory is to help make the treatment guidelines. It makes sense. The laboratory said it was 30% resistant, therefore I don't want to use that drug. So one of the most common uses that people would like to do with antibiotic resistance data is to make treatment guidelines. In short, you can, but you have to be very, very careful about it because of the biases. We have to keep in mind that in most typical circumstances, laboratories have routine samples. In a human clinical lab, in a veterinary diagnostic lab, we don't get the results from all patients and all animals. Let's take a simple example and an important common example of outpatient urinary tract infections in women. If there are 1,000 women with a urinary tract infection or a UTI, out of those 1,000 women, very few of them will actually have a laboratory sample. Most of the women will treat themselves and get better. They'll go to the local pharmacy, get an antibiotic and get better. They'll take an antibiotic from someone else and get better. Or they'll go to the hospital clinic, the doctor will give them an antibiotic, but the doctor doesn't always take a sample. So when the results are predictable, when the routine approach usually works, we rely on empiric therapy. So if there are 1,000 women with a urinary tract infection, maybe 100 of those women will go to the clinic. And maybe 50 of those women, or even less, maybe 30 of those women, the doctor will take a sample. So what does the laboratory see? The laboratory does not see data from 1,000 women with a UTI. The laboratory sees 30 results from certain women that are very particular. These might be women who have had a treatment failure. They took an antibiotic at home, they didn't get better. They went to a pharmacy, different antibiotic, they didn't get better. They went to the clinic, and the clinic says, it's time we do a microbiology test. So if there are treatment failures, if the patient is in the intensive care unit, if the patient has a complicated medical history with cancer, multiple hospitalizations, if the person is coming from a nursing home, then we may take samples from those women. So the laboratory does, hopefully, an excellent job of describing those 30 results. But those 30 results don't represent all 1,000 women. So when we talk about routine microbiology data, we have to address the fact that, number one, we underestimate how much disease there is. The laboratory might say 30 women had a UTI. And I said, no, that's not correct. There were 1,000, but most of them did not have a sample. So we underestimate how much disease there is because we rely on empiric therapy. And most patients do get better with or without the antibiotics or the antibiotics they take. So most patients eventually will get better without a sample. So we underestimate how much disease there is. but we overestimate resistance rates. If someone has a simple E. coli susceptible infection that many of the drugs will work, we often don't sample those. If the patient failed therapy with 2 or 3 or 4 agents, that's when we start to take samples. So the laboratory, hopefully we can rely on the laboratory to generate good quality data, and the laboratory can generate excellent quality data for those 30 women with a sample, and that's valuable. But we cannot generalize that to the overall population. So we might say very accurately that 30% of the bacteria in the lab are resistant to ciprofloxacin. And someone might think, oh, 30% seems like a lot of resistance. I shouldn't use Cipro. I should use imipenem, which only had 5% resistant. And that would be wrong. We don't want to jump to the reserve agents because I think Cipro would probably work. When I say 30% of the laboratory samples are resistant, that doesn't mean that 30% of the samples out in the general community are resistant. So surveillance of antimicrobial resistance does come with the risk is that we may incorrectly state that resistance is too high to the first-line agents. So there's no simple way to get around bias. We need to use the data. We can look at, is resistance common or uncommon? But the exact proportion depends on the bias. We look at trends. Resistance is going up, resistance is going down, resistance is stable. We can compare drug 1 to drug 2 to see which has more resistance. We can compare laboratory 1 to laboratory 2 to see which area has more resistance. There's no simple or inexpensive way to avoid bias. If you have problems in laboratory test quality, there are standard practices for assessment: quality control strains, proficiency testing, good training, good knowledge, good awareness. So if you have problems in laboratory test practices, we know how to assess those and to improve those. But for bias, there's no simple answer. So you can some places will do a protocol. Maybe once every 3 years, let's do a random sample of women so we do know what the correct unbiased estimate of resistance might be. But these are often resource intensive, they're time limited. You cannot do a special study on everything. So we need to utilize the routine data because they exist. They tell us about outbreaks, they tell us about quality, they tell us about relative resistance. They can be used to support treatment guidelines, but carefully. If the laboratory is 30% resistance, don't interpret that to mean that 30% of patients have resistance. It's only 30% of people with a laboratory sample. People often ask, well, what threshold should I use for deciding on drug A versus drug B? And you see some studies where they say often if it's a life-threatening infection, like meningitis, or it's an infection with great public health concern and transmissibility like gonorrhea, people often say 5%. We want the drug to be working 95% of the time, but that's only in an unbiased sample. In a biased sample, there's not an exact number. So 30% resistance to ciprofloxacin sounds like a lot, but that 30% resistance in reality might only be 10%. So we cannot have certain thresholds with unbiased data, what the threshold should be. Interpretation of biased data. It is crucial to keep in mind biases whenever we review results. We must proceed cautiously when we make conclusions and recommendations. Take a look at the time. For certain surveillance objectives, the bias is extremely important. For other uses of the data, the biases really are not so important. I'll start with high impact. I already mentioned this. Standard treatment guidelines, you don't want to recommend imipenem always, simply because the observed resistance rate to a first-line drug looks high because the true resistance is probably much lower. So biased data can have a very big impact, leading to incorrect treatment guidelines and underestimates of disease burdens. So your bias is crucial. If these elements are important for you, you might want to think about doing some kind of random sampling. Medium impact. Here, the numbers don't have to exactly be correct. The general message here is resistance is bad, it's getting worse. Some countries have more resistance than others, certain facilities, but people are not taking action on the exact number. For example, if you look at the global WHO glass maps, the country gets a color, red, green, purple. And those are very broad ranges, anything from, I don't know, anything from 20% to 30% or 20% to 40% gets one color. So if the exact estimate is wrong, the color might change. Also, they have a country like China, and one number is valuable to WHO for policy at the global level. But one number for China wouldn't make sense. The country is so large. You have areas of high resistance, low resistance, urban centers, non-urban centers. So at the global level, we just simplify to aggregate statistics. So of course we want the data to be unbiased, but it doesn't impact that global advocacy message that resistance is bad, it's getting worse. Some issues or certain areas are more problematic than others. And then lower impact. If you're looking for outbreaks, even with significant biases, the outbreaks should usually be obvious. You can look at trends. It's slowly getting better. It's slowly getting worse. The problem, this problem is more common than that problem, and quality improvement. So as I said with biases are always a concern. For treatment guidelines, the impact can be terrible. You might make a bad treatment recommendation based on the biased data. If you're talking about outbreak detection, quality improvement, you want to keep the biases in mind, but it won't usually impact significantly your ability to find outbreaks and quality issues. And that's the end of the PowerPoint. Let me just take a quick look to see if there are any chat messages. No, there are not. Oh, I'm sorry, there are messages. I've been looking in the wrong place. I've been looking at the chat thing at the top. Okay, so I will go back and look at these questions that have been showing up. My apologies, I was looking in the wrong place. Okay. Okay, I'm just going to start at the bottom. Okay. Can we link program to link these data with cross-resistance and co-resistance? The answer to that, well, in terms of multi-drug resistance, yes, and I'll talk about that with both scatter plots and resistance profiles. Will anyone from WHONET be present at ESCMID this year? That's in mid-April. Unfortunately, I was hoping to go. There is a WHO Collaborating Center meeting. However, I have another conflict in South Asia, so that we won't have anyone in Vienna for the ESCMID meeting. Thank you for the introductions. Somebody said they can't find Candida auris on the pathogens list. It is there. When you go to WHONET data entry, we show you the most common bacteria and fungi, a short list, about, I don't know, 150 or something. Candida auris is not on that short list, but it is on the long list, and we can verify that. When I get to data entry or when I get to data analysis, I will look for Candida auris, but it should be there on the pathogens list. Relevant specimen, but also timing when. And Adam, thank you for answering that. I did not notice that question. And I do see Adam has been answering some of these. The Backlink software, Phoenix, relevant specimen, but timing when, before initial. Yeah, they're important. With routine data, the idea is you were supposed to collect a sample before you start therapy. Because once you start therapy, you're decreasing your ability to find a lot of the results. If it's a resistant result, maybe it will grow. But if it's susceptible, the patient might be very sick with a strain, but the laboratory cannot grow it. So I had interesting discussions with people from Thailand. In Thailand, they have this was settled many years ago. There's a tradition. Before you start therapy for a potential case of sepsis or pneumonia or meningitis, you take a blood culture first. That's appropriate. And then they can get excellent data on the frequency of positive blood cultures and sepsis. And they were traveling around to other countries, and they were often given the unfortunate comment, we're not allowed to take a blood culture until we've already done empiric therapy. The idea is to save resources and laboratory and funds, but that's not a good policy. It means when you take the blood culture, something might not grow. And there's also the delay element. So the recommendation, especially for life-threatening infections, or for, if the patient has failed therapy, take a sample before you try something else. So, but we are relying on routine data. So we're helping with WHONET to understand the routine data. There's a bigger element about diagnostic stewardship. What samples should be taken? When should they be taken? So this is the broader concept of diagnostic stewardship. Adam, I'm going to continue with the presentation, but if you can come back to me later to highlight which of these questions you haven't answered. But I'm going to jump over to the hands-on presentation. And Adam, you can also point out things. John, this would be good if you answer this now. Okay. I've been looking at the top where it has the chat, but I forgot that that only keeps track of the number if you don't have the chat window open. I do see another question. Yeah, take sample first, then scale up or down depending on the results is one recommendation. Hello to now from Ethiopia. Thank you for joining. How and when do you set the alert thresholds and configuration of the analysis level? This is important. So the alerts are set at the time of analysis. We do have certain default alert levels, and I'm talking here about outbreak detection. Then you can reset the thresholds. So that's not at the time of configuration. There's a different alert system I mentioned for microbiology alerts. There's no threshold there. WHONET gives you a long list of alerts: quality, important resistance, important species. You can make your own alerts. So you do that at the time of configuration, but there's no threshold here. You make a rule, yes or no, to report. Good, so I'm going to go back to WHONET. I'm going to close the PowerPoint, and I'm now going to open up the WHONET software. Good. And I do a lot of tests. So this is a demo. I'm going to delete and delete. Yeah, these are all just demonstrations I was doing. That's fine. That's fine. Okay. For people, some of you may not have been on the previous presentation. Here's language and dates. If I want to change the language, I go to language and dates. I was just talking about Thailand. So if I say Thai, everything is now in the Thai language. I cannot read it. I can go to back there and I can say from Thai and I can put back to English. If I put something like Arabic, everything is now in Arabic, but what you need to do is you leave WHONET and then go back in, and then it'll be right to left instead of left to right. Oh, and I chose the Arabic for the wrong thing. Let me put Arabic here. Yeah, it tells me that here. It says, please. So now if I leave WHONET, and then if I go back in, so now it's flipped, goes the other way around. And then I go to here and I change this back to English. The software is now in English, and I forget which one it is. Okay, good. And now everything is a little bit backwards. Let me leave WHONET and let me restart WHONET. I'm a little bit confused because of the language here. Okay, let me go back into WHONET, and now everything should be back the way that it started in English. Okay. So I'm going to go to, on the previous presentation webinar, we talked about new laboratory, open, modify laboratory. So let me go to modify laboratory for just a little bit. Modify laboratory. I can choose the country name, human, animal, food. I choose the antibiotics, the sample collection locations. Those could be human clinics and wards. Those could be animal clinics, farms, markets, wild animals. They can be food restaurants, food markets. They can be water sampling sites. So location means where was the sample collected. Data fields, I can say first name, last name, animal species, food type. So those are all configurable. When it gives you a certain set, you can change it. We talked about that in the last webinar. I'm coming here now for these alerts. So if I go to alerts, WHONET gives you this long list of alerts. Here you see all of the rules. I've now chosen the high priority rules, like Bacillus anthracis is an important species. Cipro resistance is important. That's high priority, and then medium priority. Medium priority, amikacin resistant, ESBL producer, VRE, vancomycin resistant enterococcus. I can look at important species. So this is a list of anthrax, E. coli 0157, Neisseria, Salmonella typhi. For quality control, Acinetobacter is usually resistant to chloramphenicol. But as you can see in the lower right, susceptible isolates are rare. This is an intrinsic resistance. So if you see Acinetobacter baumannii susceptible to chloramphenicol, it might be correct. There might be a mutation. It's lost its intrinsic resistance. Or it might be a mistake. The mistake might be in the bacterial identification, or the error might be in the antibiotic result. So these are the alerts that we have given to you in WHONET. But you can go to new alert. I go to new, and then I can say this bacteria, these specimens. I can say call Dr. Smith. So you can decide the details of your own microbiology alerts. there's no real threshold here. You can say that it's high, medium, or low priority. I can say it's an active or an inactive rule. The alerts have been defined as important species, important resistance, quality control. You can also give a message, please call Dr. Smith, that we have a certain result for his study. Cancel. Good. So those are where you can define your own microbiology alerts. Okay, and I'm going to click on cancel, and I'm going to click on exit. Do you want to save the changes? No, I do not. Now I'm ready to proceed with data analysis. Okay, good. And I'm looking at the time. We're about halfway through, so we have plenty of time. So here I've clicked on data analysis, and you see, well, actually, let me just go to the help screen. If I'm on the help screen, you can see here the documentation. And you see here all these PDF documents with backlink and WHONET. Today's presentation is mostly here in data analysis 1 and 1, 5. All of these have to do with data analysis. So these are Word documents, and most of these documents are actually also available on the WHONET website. On the help screen, you can also look for updates. When I click on this, you can see that my WHONET is 24.14.12. There's a more recent version, so this allows me to download and install the latest version. So I don't need to leave WHONET. You can just update it from right here. If you have the most recent WHONET, it will tell you have the most recent WHONET. And then here under About, you get our email address and phone number. Not phone number, we took that off. You can see that this WHONET is from February 12th. Yeah, so that's my version, but we have another one from March that I have not yet installed on my computer. WHONET.org, my email address, help. So if you have a question for me, you can send to my email. If you have a question for somebody in our team, because I do share that would be with help, and you can choose either one. Okay, good. Data analysis. First is interactive data analysis, where you're in control. Today, I want to do this. These organisms, these filters, one per patient. We'll start off on that. Following that, we will switch over to quick analysis, which is the one-button solution. Hit the button, and you get these results on the screen, or in Excel, or in Word, or in PDF. If I click on data analysis, you saw the screen already during the PowerPoint. So let's see. Okay, so there are the 3 required questions on the left: analysis type, organisms, data files. After answering those 3 questions, I can begin my analysis. That's what I will do now, and then I'll come back for those optional features. Analysis type, let's keep it very simple. You see here at the top, isolate listing and summary, percent resistance, scatter plot, resistance profiles, microbiology alerts, and cluster alerts. So you saw examples of all of these in the PowerPoint. I'll stay here on percent resistant, intermediate, susceptible, and test measurements. There are 2 formats, a detailed format number 1, and a summary format number 2. I will demonstrate both. Detailed results. I want all the antibiotics, or I can just say certain antibiotics. There are some new features that some of you have been using WHONET for 20, 30, 35 years. I started 1989, and our countries at that time were Venezuela, Colombia, Argentina, Chile, Uruguay, France, China, Philippines, and Korea. I don't think I forgot anyone. That was WHONET. That was everybody. And now we're about somewhere around 130 countries, something like that. So let's see. There are new features. And one of those features is you can now say the CLSI recommendation is you should have at least 30 isolates. 30 is not a magic number. So WHONET, we set it at 20 just to show you a little bit more. If it's Salmonella typhi and I have 28 Salmonella typhi, it's not 30 results. It's not the magic number of 30, but 28 is still pretty good. So in WHONET, we use a default of 20, but I can change that to 30 or 35 or 40, or I can go down or up on the threshold, or I can turn off the threshold. So this is a new feature in WHONET. This is very convenient to allow you to, if WHONET had 1 result, it would include that in the output. And then in Excel, people would delete it. It was only 1 isolate, 5 isolates, 10 isolates. But by putting a threshold here, it just allows you to clean up the output. So it's less work cleaning your antibiogram before you give it to your clinicians. I will demonstrate that. It's a new feature. There are some other features I won't talk about right now. I'm going to click on OK. Organisms, I'll choose 2. In WHONET, the options appear on the left and the selections we put over to the right. So if I would like to include Staphylococcus aureus, one option is I can look for it here on the list and drag down and I look for it and there it is, Staphylococcus aureus. Oh, Adam, a tiny thing. I see we have it's a nice little teaching point. We have here Staphylococcus aureus and Staph aureus subspecies aureus. It means the same thing. The proper name is the second one. The proper official name is Staphylococcus aureus subspecies aureus, but nobody calls it that. We're busy people. We just call it Staphylococcus aureus. And you see they both have the same code. So WHONET doesn't distinguish between the two. WHONET uses the code. So I'm going to choose the first one here called Staphylococcus aureus. WHONET automatically gives it the proper current name. Okay. The second one I want to do is E. coli. So how can I find E. coli? Well, I can look for it. I find it right there. Alternatively, I can do a search. I can put Esch coli. So I can do a search at the bottom for my organism, and it searches out of the long list. When I look at the short list, the short list simply lists Escherichia coli, as well as E. coli 0157. But if I click on extended list, or if I start to search part of the genus, part of the species, when it shows me everything that matches. In this particular case, I know what the code is. The code is ECO, so I can also just type ECO. If you know the code, that's the fastest way. E. coli, E. coli. SAU, Staph aureus. Okay, good. In addition, I can, let me look for Candida auris. So if I look for Candida auris, so it is right there. The code is CRS. So I don't think that we have, let me go back to the short list. If I remove the search box here, and if I go to extended list, so Candida auris is not on the short list, but if I just do a search, C space auris, it is on the list, but I did have to do a search for it. And for future reference, maybe I will remember that the code is CRS. In addition, WHONET allows you to say all organisms, all gram-positives, all non-fermenters, all salmonella, or all mycobacteria, all parasites. So WHONET does allow you to choose individual species, like Staphylococcus aureus and Escherichia coli. WHONET also allows you to do groups of species. Very often I choose this feature called all. I will come back and do that in a little bit. These two I'm fine with. So the options are on the left and the selections are now on the right. I click on OK. Lower left data files. Ignore number 3. Ignore number 3. I was just doing a demonstration of data entry. The size of the file is 20 kilobytes. It's a very small file. That's not real data. It's an empty file. Do pay attention to these first two. The first two are called January 2020, and this is 1 month of human health data. So when I'm teaching a human health audience, I mostly use this file for demonstration. However, the One Health one I utilize when I'm teaching a mixed or an animal-oriented audience. The first database has about 622 human health isolates from a small community hospital. The second one has 400 isolates, 100 human, 100 animal, 100 food, 100 water, environmental samples. So depending on the audience, and what I often do is I'll demonstrate both. So I'll demonstrate both, but for this first demonstration, I'm going to do the human health data. I chose one file, I can choose 20 files, I can choose 500 files, I can choose 2,000 files. Choose as many files as you want. Again, options are on the left, selections are on the right. I click on OK. Begin analysis. It will first analyze the Staphylococcus aureus, followed by an analysis of the E. coli. First, I have my Staphylococcus aureus results. As you can see, WHONET is a fast software. It is a small data set, but even for much larger data sets, it's also very fast. So this is the percent RIS analysis. For CLSI laboratories, R means resistant, I means intermediate, S means susceptible. UCAS changed that a few years ago. R is resistant, S is susceptible, but I now means susceptible with increased exposure. meaning it's clinically susceptible, but if you put the dose, it might be a little bit resistant, but because of the higher dosage, the patient should respond clinically. I'll come back very soon to talk about the difference between clinical breakpoints and microbiological breakpoints. So for example, what do I look at here? The first thing I like to look at is this graph called number tested. As I said, before looking at the epidemiology and the resistance and the trends, I want to know, does the laboratory know what they're doing? And do they do it systematically? So what are the drugs they test? When I click on number tested, it tells me that we have Staphylococcus aureus tested against penicillin, sulfoxetine, gentamicin. These are appropriate drugs. I can see the drugs that they are testing. And I can see it systematic. They always test the same drugs all the time, with the exception of nitrofurantoin. Why did they not test nitrofurantoin? Maybe they ran out of discs? No, in this case, there's a simpler reason. Nitrofurantoin is a urine drug. So this particular laboratory has made the decision that they are only going to test nitrofurantoin in urine, and they're not going to test it in blood and sputum and other specimen types. So at a glance, I know what drugs they test, and I know how frequently they test each of them. I am happy with this. It looks systematic. Most drugs are tested all of the time. Nitrofurantoin is only tested in urine, and that is appropriate. I can look at percent resistant. It shows me my 95% confidence intervals, intermediate, susceptible, unknown, etc. That's the exact percent resistance. I'm going to talk about bias, and let me say, for example, penicillin. Well, let me say sulfoxetine. Sulfoxetine disc is how we find MRSA, methicillin-resistant Staphylococcus aureus. And what I can say with 100% accuracy, if I can trust the laboratory test quality, I can say 11.6% of the bacteria in the laboratory had a resistant result. That is absolutely correct. 11.6% in the laboratory were resistant. What I cannot say is that 11.6% in the general community are also resistant. We do have something here called the 95% confidence interval. This helps us statistically a bit. It says, well, you observed 11.6% resistant. If this is a representative sample, we think that the true resistance is probably between 6% and 20%. So it gives you a better estimate. So the first column, 11.6, that is the exact resistance in the laboratory samples. If we try to generalize it, the true resistance out in the community is 6% to 20% if the sample is unbiased, and that is usually not the case. So the true resistance, the observed resistance is about 12% resistance. The true resistance might be 8% or 6% or 5%. It just depends on how close the samples are in the lab, how well they represent either the hospital community or the general community outpatients. Okay. Percent resistant. I'm not going to talk about zone diameters or MIC values. So here in the lower graph, you see the percent with 6 millimeters, 7 millimeters, 8 millimeters. In the disk diffusion test, anything which is, for this particular organism, an antibiotic, anything which is 22 millimeters or larger is a susceptible result. So I can safely use sulfoxetine for these patients on the right. Here on the far left, 6 millimeters is the size of the disc. This is high level resistance. We do have this one result at 19 millimeters. There might be a quality issue. Maybe that 19 should have been 22. So maybe that's susceptible. So there might be a quality issue here with the test medium and the disc potency and the inoculum or the medium thickness. There are a lot of quality issues. This might be a susceptible bacteria where the zone diameter is a little bit too small. Alternatively, this might be true. This might be a bacteria with what we call Borsa. Borsa is borderline oxacillin-resistant Staphylococcus aureus. So the sensitive bacteria on the right, those look fine. The resistant bacteria on the left, those would be your MRSA, those look fine. The 19 millimeters here, I don't know, is that a quality issue or is it a Borsa? If you are interested, you might want to simply retest it. And if simple retesting shows the same result, you might want to go a step further and start characterizing it if it's important for you. So even with something as simple as a zone diameter, it helps you with these measurements. It helps you with the interpretation. Is this a quality issue? For example, when the medium is too thick, then antibiotic that should go horizontally goes down. So you end up with false resistance if the medium is too thick. If the medium is too thin, you end up with false susceptibility. That's right. If the medium is too thin, the antibiotic goes out further than it normally would. So there are small methodological reasons that can explain this, as well as microbiological reasons. Let me look at erythromycin. This is an interesting example. I see my susceptible bacteria on the right. I see high-level resistance on the far left, and I see moderate resistance in the middle. So the doctor doesn't really care if it's high-level resistance or low-level resistance. If it's resistant, I'm not going to use that drug. But it can be useful for infection control or molecular studies to say, well, I seem to have two different clones here from a phenotypic perspective. If I want to do molecular typing, I might want to choose some of these bacteria with 6 millimeters and some of these other bacteria between 9 and 12. So the zone number can help you to distinguish between the clones from a phenotypic perspective, which might then suggest a desire for molecular typing. Here also I have these bacteria 31, 32. That is, I don't know about hypersusceptible, but it's more susceptible than usual. It might be, 30 people like the number 30, people round numbers off. But it might be a problem of false oversusceptibility. Maybe the medium is too thin, so maybe the measurement is a bit larger than it usually would be. Okay. I'm going to show when I get to trimethoprim sulfa. This is an interesting example. I see sensitive on the right and resistant on the left, but these other sensitive ranges, it's a nice normal distribution. This is not really normal. It seems as if almost you have two populations. Between 20 and 24, looks like it might be one population. And between 25 and 30, it might be another population. It's what sometimes we call a shoulder. This is not a nice normal distribution. I'm going to show you the same graph now for E. coli. When I go to E. coli, and if I look at the same graph, you see exactly the same phenomenon, but it's more prominent, it's more obvious here. We clearly have two different populations. We have this population between 16 and 21. We have this population between 23 and 29. And you might wonder, why do I have two different susceptible populations? And the explanation is very simple. This is not an antibiotic. It's two antibiotics. It's trimethoprim and sulfamethoxazole. So my suspicion here is that between 23 and 29, these bacteria are susceptible to both of these drugs. They kill synergistically. So trimethoprim, sulfamethoxazole both target folate synthesis. So if the bacteria is susceptible to both, you end up with very susceptible. However, if the bacteria is resistant to one of the drugs but susceptible to the other, the bacteria is still susceptible as long as one of the drugs work. So my suspicion is that these bacteria between 23 and 29 are susceptible to both of the drugs, and you end up with synergistic killing. My suspicion is between 16 and 21 is that it might be resistant to sulfa, but susceptible to trimethoprim. From a clinical perspective, either drug should work, but it's good to know that the cotrimoxazole has synergistic killing for these, whereas here it's just relying on one of the two drugs. Okay. So just an example how the measurements can help you understand the populations at a deeper level. I'm now going to talk a little bit about, here in the graph, you see a couple of breakpoints for cats and dogs and humans. So these four are all ampicillin. And then for augmentin, you have the same thing. Okay, I think I'll focus on the augmentin example, amoxicillin clavulanic acid. Yep. So here's the graph for the bacteria using the human breakpoints. These are the same bacteria, but with the cat breakpoints, and here are the same bacteria with the dog breakpoints. Well, a few comments is that everybody agrees that 18 is susceptible. So in fact, they do not disagree on what the susceptible bacteria there are. On the humans, we have an intermediate range separated from resistance, but for the cats and dogs, they don't distinguish between I and R. So in this particular example, the breakpoints are very similar. They agree on susceptible. Other times, the breakpoints are quite different. I just want to have a little detour here about these different clinical and animal breakpoints and epidemiological cutoff values. There's often a misunderstanding that the purpose of CLSI and UCAST clinical breakpoints is to find resistance genes. And that's not exactly correct. The goal of the laboratory is not to tell the doctor, your patient's bacteria has a resistance gene. The doctor doesn't exactly care about that question. The doctor's question is my patient going to get better? Can I use this particular drug? So the focus of these clinical breakpoints is not to find resistance genes in a general sense. Their focus is finding resistance that's clinically important. So when the laboratory is susceptible, it doesn't mean the bacteria does not have a resistance gene. There are resistance genes that are very weak. There's a little bit of a change in the zone damage, a little bit smaller, but the patient will still get better based on pharmacokinetic data, pharmacodynamic data, the dosing that's utilized, based on animal models, based on previous human experience. So when the laboratory is susceptible, what we are saying is that this antibiotic is an appropriate treatment option, even if the bacteria is a little bit resistant. Especially things with like urinary tract infections, the antibiotic is often concentrated. So clinically susceptible means that the patient would probably get better, presuming the patient is not too sick already, but that it's an appropriate drug treatment choice. That means it's clinically susceptible. There are bacteria that are a little bit resistant that we still call clinically susceptible, but they are microbiologically resistant. And we ascertain that with what we used to call the microbiological breakpoint. Now they call it the epidemiological breakpoint or the epidemiological cutoff value. So the goal of those breakpoints is to find resistance genes from a phenotypic perspective. What is the best way to find resistance genes? Use sequencing, of course. But if you don't have the sequencing, the ECOF can help you to say, these bacteria look like they might have a resistance gene. Therefore, these, I'd like to do some molecular typing. Okay. I mentioned about the clinical impact. On the human side, we see this a few times with meningitis breakpoints and non-meningitis breakpoints. And again, we're not talking about exactly the bacteria characteristics. It's the same bacteria like pneumococcus, Streptococcus pneumonia. That same organism can cause pneumonia, can cause an ear infection, can cause meningitis. That same bacteria. If that bacteria is a little bit resistant, with an ear infection, the patient should be fine. A little bit of resistance is not that important. Even if a patient has pneumonia, a little bit of resistance is still acceptable because of the high dosing that's used. It's intravenous. We have systemic coverage. So even a little bit of resistance, we can still safely treat the patients using the non-meningitis breakpoints. But if the patient has meningitis, a little bit of resistance can kill the person. So people wonder, well, why is there a meningitis breakpoint and a non-meningitis breakpoint if it's the same bacteria? The reason is not the microbiological difference. The difference is the therapeutic difference. A little bit of resistance can kill somebody with meningitis very quickly, but the person with pneumonia, the person with ear infection should probably be fine because we can achieve much higher concentrations quickly when it's a blood infection or a surface infection than in meningitis. We have the blood-brain barrier, and the penicillin has to get through the blood-brain barrier. So we have meningitis, non-meningitis breakpoints because of the different clinical aspect. That's also why we have different breakpoints for cats and dogs and horses and fish. In fact, there are a couple of examples where there are different breakpoints for adult horses and young horses. And the difference has to do not with the microbiological resistance, but the therapeutic consequences. Good. If you're working in the human world, using the human breakpoints usually makes sense. If you're looking for resistance genes in humans, you still want to use the ECOFs. And the animal, food, water world, they're all important. If you are doing testing for sick animals, using the animal-specific breakpoints makes sense. Or if you're getting samples from healthy animals with the objective of making breakpoints for the diseased animals, using the animal breakpoints makes sense. But if you're taking data from healthy animals, from dead animals, from meat products, from water samples, there is no disease here. We're not trying to cure the healthy animal. We're not trying to cure the water sample. So in these cases, we don't care about the veterinary clinical breakpoint. We do care about the human breakpoint if we want to look at the public health impact on human populations. Also, if you have a water sample, you want to look at the impact on the human population that might get ill from the disease from the water, contaminated water. Or if you're looking for resistant genes, that's when you want to use these ECOFs, these epidemiological cutoff values. So in the human world, we almost always use human clinical breakpoints, but the ECOFs still have value if you're looking for resistant genes. In the animal, food, environmental world, all of them have value. So you need the measurements. If you don't have the measurements, if you only put R, I, and S, then you cannot reanalyze your data. So we highly recommend, WHONET is not required, WHONET does accept RIS, but we highly recommend putting the measurements. I have a little bit more to say on that, but not right now. Okay. Anything that you see here on the screen, you can copy and paste to Excel. I can save it as Excel. If I click on Save Table, and I can say E. coli, where is it? RIS E. coli. Now saving it. When it finishes, it says, oh, the file is ready. Do you want to open the file and up in Excel? Yes, I do want to open the file in Excel. There it is. Oops, sorry. The wrong thing. Well, why is my Excel not coming up? Let's see, there it is. Okay, so here you see the data in Excel with all of the graphs, all of the histograms. So WHONET can automatically make these nice Excel files. One value of Excel is it looks nicer. Another value of Excel.
I don't think we can see the Excel.
Hello, everyone. I'm back. I apologize for that. Adam, can you hear me now?
Hi, John. Yes, I can hear you now.
Great. I'm on the eastern half of Long Island, and sometimes there are problems of connectivity. This is my mother's house, so I'm sitting home for a few days. Okay, good. So I'm going to share my screen. I think I started already. Let me open WHONET.
So we have a bit of a delay, John. So perhaps if you could put your hotspot by the window, we might get a little better reception.
Well, let's see. We
still haven't been able to see your screen yet. It looks like it is trying to load, but we can't see an image yet.
And meanwhile, I'm going back to where I was. Native files. Back with the E. coli. So I'll stop sharing my screen and I'll share my screen again to see if that makes any difference. Screen. Adam, how about now?
It looks like it's trying to come through, but I still don't see any image yet. It's just sort of a black screen. Oh, okay, so I can see results. Hopefully others can comment in the chat if they're able to see as well.
Okay, and Adam, I'm doing 1, 2, 3. Has the screen updated or is there a delay?
There is a
delay, a different
but it just came through. So it looks like it's relatively working.
Excellent, excellent. So Adam, let's just continue like this. If we have trouble, I might ask you to share your screens, and then we can guide it that way. Plus we have just a half an hour left, but I'll just continue now. And thank you everyone for your patience. Okay, great. So now I was showing you the Excel. Excel has some advantages. It looks better. Nice formatting. Also, it can be automated. If you have 10 analyses, WHONET can run them all at once and send all of the results to Excel, and you can have 10 sheets in Excel. You can do that manually once a month or automatically every day. We like to set things up, automatic analyses, automatic email alerts. So I'll talk more about that later. Okay, I'm now going to go to the next to the next area. I already showed you. Adam, I'm highlighting the cefoxitin 86 isolates. Do you see that?
Not quite yet. Okay. Yes, now I see that. So there's probably a 4-second delay.
Right. So there are 86 isolates in this database of Staphylococcus aureus, and 11.6% of them are resistant. However, how many people is that? I don't know. It's 86 isolates. I'm going to click on continue and continue. And now I'm going to click on one per patient. Adam, can you see the main screen, one per patient?
Not yet.
Okay, I will wait. So I'm back on the WHONET main analysis screen.
Now we see the main screen, yes.
And in the top right, you see the button that says one per patient. I will click on that. And after the delay, you will see there are three options: by isolate, by patient, or let me call it by episode, that use the time interval or the resistance profile. I'm going to click on the second option called by patient. So Adam, can you see that screen now by patient?
We see the one per patient screen, but it's still checked by isolate. So there is perhaps a 10-second delay now.
Okay, sure. So I have clicked on by patient, and below it, there are several options. One of them is first isolate only. The second is first isolate with antibiotic results. So I'm choosing that option called first isolate with antibiotic results because I'm doing an antibiotic analysis. There are other options on this screen. I can do first isolate per quarter, first isolate per resistance pattern. I can choose most resistant, most susceptible. So we offer a variety of ways of defining what I mean by one per patient. But for routine normal use, we either use first isolate only if we do not care about the antibiotic results, or first isolate per patient with antibiotic results. For example, if you're looking for outbreaks of fungi, we don't usually do susceptibility testing on fungi. So first isolate only would be more appropriate in that circumstance. Okay, now I'm going to click on OK to go back to the previous screen. Without waiting, I'm just going to. What's that?
Looks like it's working a little bit faster now. We can see your mouse moving sort of in real time.
I'm clicking on begin analysis. And before I showed you, there were 86 isolates, and 11.6 of them were resistant. But those 86 isolates came from 76 people. So about 10 of the isolates, most people had Staphylococcus aureus once, some people had it twice, some people maybe 3 times. So when I remove the repeat isolates, it is now 76 isolates from 76 people with 10.6% resistance. So it does have an impact on the resistance rates. When you have few repeats, it's a small impact. When you have a large number of repeats, it will impact the results to a larger degree. I saw one database where 40% of the isolates were MRSA, but only 30% of the patients had MRSA because MRSA was tested over and over again. I'm going to click on continue. I'm now back at the main screen. I'm now going to go to analysis type and put number 2, summary. When I click on summary and I click on OK and I click on begin analysis, Adam, do you see my output table?
We briefly saw it flash there. I think we still see you setting the options, and now we see the output.
Okay. I'm not going to stop on every screen because of this delay, but hopefully by now you've seen it's very straightforward. So now in the output, I asked for E. coli and Staph aureus, so I have 2 rows. Here, I do not see the percent R and I and S. I only see the percent S. This is more related to what we call the antibiogram. There were 71 people with E. coli, 76 people with Staph aureus. I see my percent is sensitive. And when I scroll over to the right, you see that amikacin was tested 7 times. Cefotaxime was tested 70 times. So some of the organisms were tested 76 times, but other were only tested 7. So I'm going to go to continue and show you that feature I mentioned. I'm going back to analysis type. And Adam, let me know when it catches up.
Okay, not quite yet.
Okay. So WHONET was showing me statistics with 7 results. I don't want to tell those results to the doctor. 7 is too small. It's not reliable. Sometimes it's only 1 result. Sometimes it's 5 results. WHONET will show you if it's at least 20, you can change it to 30 if you would like. So what I did here is I'm just checking on the feature called minimum number of isolates.
And
So
I think
Adam
we're
has,
caught up with you now.
right, so you see here, lower left, minimum number of isolates is 20. Okay, begin analysis. And now you see the same graph, the same table, except all of these numbers are 20 or larger. So WHONET has automatically deleted antibiotics with only a small number of results. Okay, good, continue. I'm going to go to isolates, and I'm going to show you the options for filtering. I just showed you an antibiogram for Staphylococcus aureus and E. coli, but maybe I want to repeat that with only urine. So I'm going to go to isolates. Adam, has it caught up on the main screen?
Now we're looking at you're about to click isolates.
Great, I'll click on isolates. And from this screen, I can say male, female, intensive care unit, medicine, surgery, imipenem resistant, oxacillin resistant. So in this particular example, I'm simply going to say specimen type. And I click on the option at the bottom called Define Criteria. And WHONET is asking me, what kind of specimens do you want? And I can type UR. UR is the code for urine. But in fact, WHONET has many codes for urine. So here at the bottom, I've done a search for urine. And WHONET does have about 10 different codes for urine from bladder, urine from kidney, catheterized urine, non-catheterized urine. Adam, can you see the different kinds of urine?
Yes, and I see that they're all highlighted.
Yes, I can include those if I want only the urine, or I can exclude those if I don't want the urines. I can use this arrow key in the middle to say all of the urines. I say OK. I say OK again. And now I'm back on the main screen. Staph aureus, E. coli, but only urine. Just waiting a little bit for the delay. Adam, that's OK?
Yep, I think you can proceed.
Begin analysis. You see the exact same thing. You see that the
Yes,
okay.
we can see.
And you see one row here for E. coli. You don't see Staphylococcus aureus. One reason is that maybe there are no Staphylococcus aureus in urine. That is not the case. As you saw earlier, there are some nitrofurantoin results. However, there were no Staph aureus antibiotics that met the minimum threshold of 20. So with a minimum of 20, we only have results for E. coli. Okay, good. I chose Staph aureus and E. coli. Normally, I would not put those 2 bacteria into one antibiogram. I would say something like all gram-negatives. Yeah, sure, I'll do that now. I'm going to say clear the list. Adam, can you see I'm on the organism? And I have clicked on the left on gram-negative organisms.
Yep, it looks like it's catching up to you a little bit faster now.
Okay. So on gram-negative organisms, I will select that. I click on OK. And then I begin the analysis. Okay, in fact, only E. coli came through. It's only 1 month of data. I'm going to remove the threshold. Okay. Now you see many bacteria. Well, once it catches up. There were 50 E. coli in urine, 13 Pseudomonas, 12 Klebsiella, etc. And of course, if I set a minimum of 20, all of these will disappear. So this is my gram-negative antibiogram. Adam, everyone can see that?
Yes.
You click on continue, and I'm going to show you this feature called macros. So I'm going to click on macros. I have a lot of macros because I've done this before. You would normally have a normal list. I want to make a new macro, and I'm going to call this my gram-negative antibiogram. You give it a meaningful name. I click on Save Once to save the macro name. I click on Save Again to save the file. So now here on the list of macros in blue, you see my gram-negative antibiogram. Oh, I forgot to say in urine. Okay, it's my gram-negative antibiogram in urine. Now that I've done that, you saw it's very easy to make a macro. I can exit again. I have just left the WHONET analysis screen because I want to show you why I made a macro. I can come back now, I can come back next month. I go back to data analysis, and I am now back in the data analysis screen. Adam, can you see that?
Yep.
I have a blank screen here. Lower left, I will click on macros. And here is the macro that I just created. So it remembers, I'm going to click here on the right where it says load. When I click on load, it remembers those details. First per patient, urine, gram-negative, the name of the file, the name of the analysis. So you can imagine that you can have one macro that you want to repeat once a week, once a month, once a year. In fact, you might have 10 macros, and these 10 macros become my weekly report. These 20 macros become my monthly report. You can have one report for the pharmacy, a different report for infection control, and they rely on these macros. So you make the macros and you save them however you would like with the thresholds that you have set. Okay, I'm now going to continue with a different kind of analysis. I will go to analysis type and show you the isolate listing and summary feature. And I'll just wait for the screen to catch up. So I'm on the analysis type screen. We have been looking at the second option, RIS. Now we'll look at the first option, listing and summary. I'm only going to show you 1 month of data. Here on the right, it says specimen date by month. I'm going to put by day because I'm only going to show you 1 month of data. Okay. So I want to see the list of the bacteria. I want to see the summary, so I want to see both. I want to see the distribution by day. I want to include my microbiology alerts, and I want to include my cluster alerts. There are thresholds in here. If you want to change the thresholds, you can do that here. I can say, okay. I don't want just the urine. I want the list of everything. So now I'm on the main screen, and I see gram-negative organisms on the left. I see isolates, urine on the right. I'm going to click on isolates because I don't want to see only the urine. I want to see everything. Here at the bottom, it says clear all criteria. When I click on clear all criteria, do you want to clear all of the criteria? Yes. And I will say okay. So now it will do all the gram-negatives. But I don't want all the gram-negatives. I want everything. So I'm going to go to organisms. I'll wait a little bit, and on the top right, it says gram-negative organisms. Above gram-negative organisms, it says clear list. So when I click on clear list, gram-negative organisms will disappear. On the left side of the screen, it says organism groups. And I can double click on all organisms, so I can look for outbreaks for every organism. I'm going to say okay. I'm going to say begin analysis. And Adam, let me know when people can see the output screen.
Yes, we can see it.
Perfect. So here you see the bacteria in alphabetical order. This top block here is Acinetobacter baumannii. You see the patient details on the left. If I scroll down, eventually you'll see that some of these appear in red. Let me go a little bit more to the right so you can see more in red. So anything in red is unusual or important, unlikely, and those are the alerts. Let me go up there. There's another section. Yeah, here's the section I'm looking for. Here you see a lot in red. This means alert. If I move over to the right, you'll see they are categorized as high or medium alert. You'll see a little bit further to the right that some of these are quality control alerts. Some of these are important species alerts. and some of them are important resistance alerts. For example, carbapenem non-susceptible is a high priority resistant alert. On the other hand, if I scroll on important species, here is Cystinia trophomonas, Neisseria meningitidis. These are important species. Okay. So these can be WHONET alerts or alerts that you have created yourself. I'm going to click on continue. And Adam, can they now see the summary?
Yes.
In the listing, you saw a table with 600 rows, one for each isolate. Now you can see a summary. For example, E. coli, and I still have one per patient, 71 isolates from 71 people. And if I look at the distribution, there's E. coli almost every day. Haemophilus, every couple of days there's a Haemophilus. But if I look at this organism, diphtheroids, you see there's a large peak at January 25th. There were 7 people on the same day with this organism. So this is an example of WHONET's outbreak detection capabilities. WHONET is integrated with SATSCAN, so we can see that most days there are 0 or 1 or 2 people with this organism, but then 7 people have this on one day. Personally, I don't think that's an outbreak. Diphtheroids do not usually cause outbreaks. They're not very pathogenic organisms, but they do cause a lot of contaminations. And these are real data. I did not invent these data. These are real data. These to me look like a potential issue of contamination. 7 people on the same day with diphtheroids, are they sick? What was the sample type? These might be contaminations. Contaminations are also important. They're not disease issues, they're quality issues. There's a different organism here, Klebsiella pneumonia. This looks more like a real outbreak. There were, at the end of the month, 2 people, and then 3 people, and then 5 people. This looks like it's a potential outbreak. What other information would I like to know? I'd like to know what room they were in. Were they in the same room? Were they in outpatients? Were they in inpatients? Did they have the same resistance characteristics? What were the specimen types? So WHONET will not tell you you have an outbreak. WHONET will not tell you you have a contamination issue. WHONET will tell you this is more than I would usually expect. Then it's up to you to decide if you want to investigate and control the issue. If I sort the column cluster number, you can see there are only 2 bacteria that had a statistical detection of clusters. Okay, good. The other organisms, there's no statistical evidence to suggest a cluster. That doesn't mean there's not an outbreak, but statistically, it is reasonable variation. I'm going to click on continue. And I can look for outbreaks specifically in blood. I can look for outbreaks of imipenem resistance. You can change the outbreak selection criteria. We've done many publications about WHONET outbreak detection in the hospital setting, and a few in the community setting, like I showed earlier with the Shigella. Let me go to analysis type. So I just showed you isolate listing and summary, including these microbiology alerts. So we don't need to review that again. And the cluster alerts. So you've now seen RAS and test measurements. You've seen isolate listing and summary, including microbiology alerts and including cluster alerts. When I did it here, it showed me all 600 results. If I do the same thing here with microbiology results, it doesn't show me all 600. It just shows me the few that have an alert. Okay, good. I'm not going to show you the scatter plot because of time. I showed you an example in my PowerPoint. I do want to show you the resistance profiles. It's very similar to a normal listing, but it includes the multi-drug resistance pattern. I can see the list. I can see the summary. I can see the specimen date by month, but it's only 1 month of data, so I'm going to change that to day. There are other features that I will not talk about now. Okay. I don't want all the organisms. Well, no, I do. I do want to look at all the organisms. No, I'm sorry, I don't. Not for resistance profiles. I don't want all the organisms together. I only want to look at the Staphylococcus aureus. So for the code, I put Staph aureus. For all organisms, I can remove that from the list. So now WHONET will only look at Staphylococcus aureus. I will say OK. I can say ICU, I can say blood, I can say MRSA, but I won't do that. I will simply say Staphylococcus aureus. Begin analysis. Here you see a list. It's very similar to the list I showed you 2 minutes ago, but there are a few additional columns here. Here you see a column called resistance profile, and here you see it's empty. That means that these bacteria are susceptible to everything that I requested. What did I request? I requested penicillin, erythromycin, clindamycin, cefoxitin, gentamicin, SXT, and Cipro. You get to choose which antibiotics you want to look at multi-drug resistance. For example, with tuberculosis, there are standard definitions for MDR, XDR, TB. People do not use every antibiotic that was tested. They use a certain set that they thought was interesting and standard. So here I have chosen these drugs to define my resistance pattern. These bacteria are resistant to one drug, erythromycin. These bacteria are resistant, and there are many of these are resistant to one drug, penicillin. Resistant to two, resistant to a different two, resistant to two, resistant to three, resistant to four, resistant to five. There are three at the bottom that are resistant to everything. And by everything, I don't mean vancomycin, I don't mean linezolid. I mean they're resistant to everything that I requested. Those 7 drugs that you see at the top of the list. If I look at those 7 results, let me go back to the left. Very interesting. You see that 2 of them were in oncology. Adam, did it scroll over? Can they see the oncology now?
Yes, I think it's moving much faster now.
Great. So 2 of these are oncology patients. So I am not too surprised to see multi-drug resistant MRSA in oncology, these last 2. There's also one in the outpatient setting. You might think that's strange. Why do I have a multi-drug resistant patient in the outpatient setting? Well, keep in mind that not all outpatients are healthy people. Some of them might be oncology patients who went home. Some of them might be a family member. Some of them might be nursing home residents. So these last 2 people in oncology have multi-resistant MRSA, and I know what the risk factor is. This patient also has multi-resistant Staph aureus. I don't know what the risk factor is, but if I discussed with the patient, if I reviewed their medical chart, then I could find out what their risk factor might be. WHONET also has these columns called MDR, XDR, PDR. WHONET looks at multi-drug resistance in 2 ways. There's the one I'll call the WHONET way. WHONET says these are exactly the drugs. These are, oh, sorry, I accidentally moved the column. These 2 bacteria are resistant to these 4 drugs. These bacteria are resistant to a different 4 drugs. That's one way to look at multi-drug resistance. Focus on the exact drugs. These other columns called MDR, XDR, PDR are using a publication that I'm a co-author on from the ECDC in Europe with proposed definitions for MDR, XDR, PDR, where we don't look at the exact drugs, we look at how many classes. Is resistant to 1 class, 2 classes, 3 classes? So that's a different way. I like the WHONET approach if you're doing outbreak detection. For outbreak detection, you want to know which drugs are resistant and sensitive. The ECDC way, I think it's more for advocacy, awareness. Multi-drug resistance is important. It's an important public health threat, a therapeutic threat. So the focus is not on exactly which resistances, but how many resistances. I'm going to click on continue. That's the list. And now this is the summary of the list. For example, here, it's resistant to everything. I showed you that. There were 3 patients. 2 on January 13th and 1 on January 6th. I forgot to turn on the outbreak detection features. I won't go back and do that now, but I could have clicked on include outbreak detection alerts. This one would generate an alert because there are 3 people on the same day. These are Staphylococcus aureus resistant to 1 drug, erythromycin. In the whole month, there were 3. And all 3 were on the same day. This might be an outbreak, it might be a contamination issue, it might be one family that came in together. So WHONET can look for outbreaks on the basis of the species, like diphtheroids and Klebsiella that I showed you, but WHONET can also look for outbreaks on the basis of the resistance pattern. Here is one example with erythromycin. I showed you the earlier example with Shigella sone, non-susceptible to SXT. I'm looking at the time. We're now at 9 o'clock. I'm going to look at a number of the questions, but I also know some of you may have to leave. It's either early in the day or late in the day. I'm going to click on exit. We covered almost everything. I didn't cover, Adam, can they see the main screen now?
Yes.
Good. There's this feature on data entry called combine, export, or encrypt data. If you have 12 files, if you have 12 monthly files, you can combine them together if you want. If you have data from 20 labs, you can combine them into one big file. That's combine. You can encrypt. For example, I'd like to share my data with you, but I don't want to send you the patient's name. I don't want to send you their birth date. I want to hide some of the information. So the purpose of encryption allows you to share the data with other people, but you don't want to share everything. Maybe you just want to share the blood. Maybe you just want to share the CRE. Maybe you do want to share the specimen number, but you don't want to share the patient's name. So this feature allows you to combine files together, encrypt files, or export. So for example, here I can say I want to combine all three of these together. I can say all three files. Adam, can they see that I'm selecting those three files?
Yes.
Thank you. And then I can combine them into one WHONET file, or I can export them to WHO GLASS, or I can export them to FAO InFARM option A, which is isolate level reporting, or option B, which is aggregate statistics reporting. And just given time, I'm not going to focus on that now. We already have a webinar that's on our website about exporting to GLASS. We'll repeat that at some point, probably, and FAO. So we'll have some future time, a specific webinar on FAO reporting. We have done InFARM training for in Colombia for Latin America, in Zambia for Africa, in Thailand for Asia Pacific. So FAO is coordinating a series of trainings, and this first year they were very successful. I think they had 29 countries submit antibiotic resistance data to InFARM, and they only went live in June, so they considered it a great success, and most of the data were prepared with WHONET. So as I said, this screen is for combining, encrypt patient information, or exporting to the European network, EARSnet, the WHO GLASS modules, and the FAO modules. So I'm not going to show that because of time. The final thing I think I would like to show you before I go to the questions and answers, and many of you might want to drop off at that point, is I'm now back on the WHONET website. Okay. Adam, they can see that?
Yep.
And I'm on the page called webinars. I just want to highlight that today was to focus on antibiotic analysis in a variety of ways. We already had September 2023, a full 2 hours dedicated to WHO GLASS reporting. So if that's an interest for you, I recommend you look at that one. We did that, part of the time was me, and part of the time was Barbara Tornimbene from WHO. October, I didn't even get to show it all today, the quick analyses. I won't do it now because of time. But we did a full webinar about the quick analysis, Word reports, Excel reports, so that we have a webinar on that. Today, I talked a bit about multidrug resistance to improve outbreak detection, that MDR, XDR, PDR. We have a full webinar on that. We had 2 webinars about outbreak detection. So basically, today was sort of an overview of the different WHONET analysis features. But we have 2 hours dedicated to some of these more important ones, especially macros, multi-drug resistance, and outbreak detection, and GLASS reporting. Adam, if you could start organizing the questions for me, that would be very helpful. While you do that, I'm going to go back into WHONET. Adam, can they see my screen? I want to click
Yes.
on quick analysis.
Yes, I think it's caught up now.
Great. So earlier we looked on normal data analysis where you are in control. I want to just spend a few moments on quick analysis. I just want to choose report number 2, organism and antibiotic statistics. If I go to data files, I can choose, I'll choose both the animal data and the human data. They'll be mixed in together. Okay, I have just selected those 2 files. I select OK. And then I say begin analysis. And as you can see, it will do a series of about 10 analyses. Number 1 is organism by laboratory. And in the graph, I can see the graph of the different bacteria. This is a mixture of human and animal. If I click on continue, I can see the distribution over time. Useful for looking for outbreaks. If I click on continue, I can see the difference between male and female. And again, this includes human and animals. For example, E. coli, not a surprise, is much more common in the food than in the men. I'm sorry, female. So E. coli is much more common here in females than in men. That's obvious, urinary tract infections. A lot of them are unknown. That would be the food samples and the water samples where there's no gender. Okay. If I click on continue, I now see the age distribution. I won't show all of these. I'll click on continue. This is the precise location. So for example, there's an interesting example here with Stenotrophomonas multifida. E. coli is most common in the outpatient. Stenotrophomonas multifida is most common in the surgical intensive care unit. So this seems like a local hygiene issue. So all of the other rooms of the hospital, the Stenotrophomonas multifida is particularly common in the surgical ICU. This is valuable information for the infection control team. This is what we call the location. This next one is what we call the location type. For example, the location type, if I look at E. coli, most of it's unknown. That would be the food and the water samples, but then followed by inpatient, followed by outpatient. For the Stenotrophomonas example, Stenotrophomonas, again, is mostly the ICU. If I click on continue, I now get the distribution by specimen type. For example, E. coli, not a surprise, it's mostly urine and water and stool. Those would be the food, the animal isolates would be stool. If I look for Haemophilus, Haemophilus is mostly sputum. If I look for coagulase negative staphylococci, it is mostly blood, but a lot of that would be contaminants. Some of them would be wound and urine. When I click on continue, I now have the detailed report by Staph aureus, and you've already seen this graph. This is the Staph aureus percent resistant, intermediate susceptible. Here I see the erythromycin that you saw earlier. When I click on continue, you can see what we saw earlier, the trimethoprim sulfa. This is the detailed report. Continue. This is the gram-positive antibiogram. Continue. This is the gram-negative. I'm not showing you all the details because you've seen a number of these before. You did see this one before. This is the gram-negative antibiogram, and you can see it's mostly E. coli, followed by salmonella, and a lot of that is the food and the animal studies. So that's to show you the value of a quick analysis. The final one is number 4, epidemiology report, begin analysis. In the lower left, WHONET is running a lot of analyses for outbreak detection, specimen types, important resistance, WHO GLASS reporting, and it's going to save the results to a nice Word document. So as I said, we have a full 2 hours dedicated to the subject of these standard reports and macros, but this is just that introduction. If you find this interesting, I refer you back to the 2-hour webinar we gave precisely on this topic. In the lower left, if your screen is caught up, WHONET has finished the analyses. It is now making the Word document. It's doing the antibiotic results, it does the WHO GLASS reporting, and the last page of it will be an antibiogram page. On the screen above it, you see number 11 is antibiogram. That's new. So many of you have not seen that yet. We only put it in January. WHONET has an antibiogram I will show you right now. It'll have a single gram positive antibiogram and a single gram negative antibiogram. Number 11 goes beyond that. It does antibiogram by male, female, by age group, by ICU. So the idea is to not only give you one antibiogram, but a variety of different antibiograms, to meet your different stakeholders. At the present time, that is an Excel report. It gives you a nice Excel document with all these antibiograms. We will start work to do a Word version. The Word version will have less detail, but it's more attractive and easier to share with your colleagues. So it's nice to give them an Excel report, but sometimes they don't want all that detail and they want the nice reporting that they can get with Word. It has finished the analysis. It asked me if I want to analyze and open the file. I say yes, and it is now open. I'm going to zoom out here a bit. So I'm not going to go in any great detail, but here you can see a lot of the analyses you've seen already, but instead of showing you 80 bacteria, it just shows you the top 10. It doesn't show you all the locations, it shows the top 10. Here we see the distribution of male and female, we see blood, we see MDR resistance. Here in red, orange, and yellow, we see the WHO GLASS priority, critical, high, and medium priority. Here we see examples of outbreak detection. And on the last screen, I'll zoom in on that. You see the antibiogram that I mentioned. It's a single antibiogram, gram positive at the top, gram negative at the bottom. The new report I showed you would have all those different kinds of antibiograms in the form of an Excel document. And we will make a similar one as a Word document. So I'm going to stop sharing my screen. For those of you who do have to drop off, thank you for your time. I apologize for the technical issues.